Hey guys, this is Carrie, and in this video I thought we could take a more detailed look at the virus spread project that we did in the last one. Not necessarily too much coding, but just looking at how this model is really useful. So let's look at what happens if we have 10 people. So if we have 10 people, it looks like maybe we start off with one person that's sick, and then because there's so few people, they don't get a chance to interact with too many people. So we end up the disease ends up not spreading too fastly because they don't get to interact very much. So in small communities like this, with a lot of space in between people, maybe this is like, I don't know, a mountainous community where people don't interact very much and they've got their homes pretty far apart from each other. People don't interact very much, and it ends up being that the disease doesn't spread very quickly. So let's look at that again. So even though this person's been sick for a long time, they haven't actually hit anybody until they get cured. So in general, it's not that dangerous. But if we look at creating a more city-like environment where we have more people packed into the same area, more interactions, maybe we have 200 people in the same space now. Let's see how things change. So this disease was actually a lot more deadly. Instead of having 1 or 2 people die out of 10, which would be a 10% or 20% fatality rate, here 98 people died out of a possible 200, which is almost a 50% fatality rate. So having this increased congestion in the city was incredibly dangerous because the number of collisions actually increased. So let's see if we do 100 instead. It was a little bit even hard to see. It was so congested there. What we're expecting here, I think, is less than 50% will die, but let's see. All right, so here we go. Out of 100 total people, 37 died here. So yeah, it was less than 50%, but it was a lot more dangerous than the example where we had only 10 people. So this is one of the reasons why we're practicing social distancing right now, is the fewer interactions that we have with people, the less likely chance we are to spread the disease, which in turn makes our whole population a lot safer. Another thing that you could look at is, kind of to me, social distancing might be, instead of like having the total number of people change, you might have the same number of people, but the speeds might change. So with social distancing, people are going to move around a lot less. So why don't we make it so that this dot speed, instead of being equal to 6 minus 3, this is going to be equal to, I don't know, 1 minus 0.5 and 1 minus 0.5. And this number is just mathematically, it always has to be half of this one. So let's see if this is saved, and let's see how this reduces the spread of the disease. So here, 37 people died. Here, people are moving around a lot less. And so it gives people a greater time to get healthy. And here, only 20 people died because we were practicing social isolation. Social distancing, not social isolation, sorry, social distancing. Let's do another simulation here. And here, even though this person's sick, because they're not moving around too much, they have a really good chance of getting better before they infect anyone else. So here, only 16 people died. If the reverse happens and people move around quite a bit, so let's have everyone moving at a speed of 10, then let's see what happens here. The disease is far more deadly because everyone has more interactions with each other. So here, because people are moving around a lot more, over 50% of people died. So I think this maybe lends some credence to like this idea of social distancing and why it's so important, and our simulation backs that up. A couple of other variables can change, right? You could start off with fewer sick people here, or you could start off with, different probabilities of getting well and different probabilities of dying. So if we increase the probability of getting well to a 5% chance of getting well, what we should notice is that the disease is not very deadly at all. So here, even with no social distancing, because people quickly get better from the disease, only 5 people had a chance to die before the disease was completely eliminated. So I think it's interesting to play around with this model. Of course, these variables are not set by us in the real world. These variables are set by the disease itself. And so I hope you guys found it interesting to play around with these and not too morbid. But these simulations really show kind of the power of computer modeling in backing up some of the political hypotheses that are out there nowadays. All right, so talk to you guys later. Bye.